So our research group here has two foci. One is Earth observation, that's basically remote sensing of the land and the atmosphere. And also we study landscape fires on Earth and their impacts and their magnitude. And sometimes those two things come together, and so we study fires through the process of Earth observation. So one of the things we're really trying to do is to understand and quantify the role of fire in the Earth system, and that includes its effect on the land and on the atmosphere. And we need a whole bunch of diverse skills to do that, and we're relatively unusual as a group because we have people doing satellite retrieval algorithms, field work, airborne validation campaigns, and laboratory studies, all working together in order to meet this single aim. So one of the things we study most commonly is landscape fires on Earth, and though you might hear about them in places like Southern California or Southern Europe, because these are close to population centres, they're actually really ubiquitous across most vegetated environments, and they in fact burn an area the size of India or larger across the Earth every year typically. So fires, as well as burning lots of material on the Earth's surface, they release much of that material into the atmosphere in the forms of particulates or trace gases. Some of these are greenhouse gases, others are air pollutants, and we need to understand what effect these are having on Earth's atmosphere and its air quality and climate. One of the challenges with studying fires from satellites is that fires change dramatically over quite short periods of time. So we often use geostationary satellites which image the Earth very, very frequently in order to provide really regular updates on the information. So Earth observation satellites are mostly not specifically built to target information on landscape fires. So one of the things our research group here does is convert raw data from satellites into information on landscape fires through the writing of computer-based algorithms. Deriving information about fires while they're still burning from satellite data is both where they are, when they're burning, and also how much heat they're putting out, because that can be used to estimate what they're putting into the atmosphere in terms of smoke. So once you've written an algorithm that turns raw satellite data into information, you want to test its accuracy, and you can do that either by comparing it to already evaluated satellite products or to data from airborne surveys that can typically be much more accurate and spatially detailed than satellite data itself. And what we often do is fly the airborne survey above our target fires at the same time the satellite is going over, and then comparing these two separate pieces of information to make sure they agree. These airborne survey campaigns are quite challenging. You're having to pack the aircraft with a whole bunch of imaging equipment that is very sophisticated, and then you have to operate that in a place typically you've never even been before. So our recent campaign in Canada was aimed at validating the Sentinel-3 SLSTR satellite product that we're developing for fires. We took the aircraft, packed it with a bunch of instruments that are measuring at similar wavelengths of light as SLSTR, and we flew above forest fires whilst the satellite was going over in order to be able to compare the rate of heat output measured by the plane and the satellite and evaluate the quality of the satellite product. So we run other airborne campaigns beyond those associated with landscape fire information. So much of our research capability is based around use of thermal infrared data, and that's not only for landscape fires but also, for example, for land surface temperature. So based at Duxford Aerodrome, we've recently worked with NASA Jet Propulsion Laboratory to use something called HITEST, the Hyperspectral Thermal Emission Spectrometer, and that's an airborne instrument unique in the world. And the funding for the campaign came from NASA and also the European Space Agency, who are interested in the data because it's going to underpin some of the design of a potential new satellite mission. And we have people in the field who deploy a whole bunch of ground-based instrumentation in order to supplement the data from the airborne campaign to validate the HITEST-derived land surface temperature measurements. So here we have the capability to run airborne survey campaigns primarily for science purposes, not only for us, but also for other members of the community who want to access that type of information. So as well as developing and using satellite data for the study of landscape fires and other environmental phenomena, we also do a lot of field work, and that's important for two reasons. One is to evaluate the quality, accuracy and precision of the satellite-derived data itself, and the other is to collect information that you can't get from satellites. We've done a lot of field work in Africa. It's the most fire-affected continent on the planet. It has huge areas of savanna grassland that actually are maintained by landscape fires. And if you really want to study fires on Earth, you really got to be working in Africa. So one of the great places to study fire in Africa is actually Kruger National Park. They have a very long-term fire experiment there, been going on for around 50 years, where they have burn plots of about 7 hectares in size, dozens of them, and they burn these at different frequencies. And one of the original aims was to understand how often a savanna landscape has to burn in order that it's maintained as a savanna. So some of these burn plots where fires have been excluded look like forest, whereas some that burn very, very frequently look almost like just grasslands with the occasional tree. So one of the things we're using Kruger National Park burn plots for is to validate the satellite products of fire. For example, collecting data from a helicopter whilst the satellite's coming over and comparing the two. And we're also using them to study how the emissions from fires to the atmosphere change over the season. In Africa, we're generally studying surface fires that are consuming herbaceous, grassy type fuel mainly. In Canada, we're mainly studying boreal forest fires. These are high intensity crown fires often that are consuming huge amounts of fuel above the surface. And in Indonesia, we're studying mainly peat fires, where the fires are actually often burning material below the surface of the land. Unlike most landscape fires around the planet that mainly burn surface fuels, fires in Indonesia actually are often burning down into the organic soil, which is very carbon rich and can burn when it's dry. So the types of underground peat fires you find in Indonesia, for example, are both extremely problematic for air quality because they burn in a way that really maximises the production of particulate-laden smoke, and also they're quite difficult to tackle because most of the combustion is actually occurring below the surface. One of the challenges for satellite observations of Indonesian fires is the intense amount of smoke they emit. It can provide a barrier to mapping things like burned area, which is one of the reasons why we focus largely on infrared methods, which sees through the smoke and can see the fires while they're still burning. So we're collaborating with local scientists in Indonesia, for example, who are interested in the health effects of these fires. So whilst they're studying, for example, pregnant mothers and their babies and some of the health issues that they may suffer, we are providing information on the exposure of these different population groups to smoke. So we established a combustion chamber facility outside London. That's for two reasons. The first is to be able to test equipment under the conditions we might find when we go overseas to do field work, but in ways where we can understand the calibration of the equipment and make sure it's performing well, particularly as much of the equipment is not really designed to work in the rather extreme conditions that we might see in the field close to landscape fires. And the second reason is that in the chamber we can perform replicated experiments, slightly changing the measurement conditions or the conditions of the fuel, and even sometimes deploy more sensitive instrumentation than we are able to do in the field to really understand what the fires are doing and also what the chemistry of the smoke is. So our research group is quite unusual because we have the capability to write satellite retrieving algorithms, do fieldwork to validate the output of those algorithms, and to run airborne campaigns to contribute to that as well. And all this information comes together in terms of landscape fires.